Hi everyone! In today's lesson, we're going to be going over apparent weight and we're going to be doing a few more free body diagrams in 2 dimensions as well as some more word problems. Okay, so let's start off with apparent weight. Apparent weight isn't necessarily exactly your weight, but it is what you feel you're weighing. Like for example, if we were going in an elevator, sometimes we feel heavier in an elevator when it's going up, or sometimes we feel lighter in the elevator. We can explain apparent weight with physics in a simple free body diagram and net force equation. Remember that apparent weight is also equal to your normal force, because the normal force that we feel is the weight that we feel as well. So if our normal force is less than our actual weight, then we feel lightweight. If our normal force is greater than our actual weight, then we feel heavier. So let's get into how normal force can be greater or less than our gravitational force, which is going to be our weight. So let's say that this is you standing on a scale in an elevator. So this is your center of mass, and there's a force of gravity acting downwards upon you. From the scale, there is a normal force acting up. If this elevator is not moving, then you're not moving either, and N has to equal to mg in order for the net force to be 0. But what if the elevator is accelerating upwards with an acceleration of a? So, something really important to keep in mind is that since we are in the elevator, we are in the system of what we call the elevator U in the scale. And because the elevator is accelerating upwards and you are inside the elevator, then you are also accelerating upwards at an acceleration of a. This means that if we take upwards to be positive and downwards to be negative, our F-net equation has to result in our mass times the acceleration a. So since we only have y components, our F-net equation should look something like this. N minus the gravitational force has to result in m times the acceleration. Remember once again that apparent weight is equivalent to the normal force we experience. And so solving for n will give us ma plus mg. So since a is positively upwards, the apparent weight we experience is heavier than our actual weight. So the normal force that acts upon us is greater than our usual gravitational force that we're used to experiencing. Now, what if the elevator was accelerating downwards at an acceleration of a? Once again, because we're in the system of the elevator, we will also be accelerating downwards at an acceleration of a. This means that our F-net equation has to look something like this. N minus mg has to equal to negative ma, because a in this case is negative. So solving for n, we get mg minus ma. And that is why if the elevator is accelerating downwards at an acceleration of a, we feel lightweight because our normal force is ma less than our usual mg that we're used to experiencing on a surface. So, from both of those two accounts, we can take the general equation of n in an accelerating elevator as mg plus ma, where a can be either positive or negative, and simplifying this, factoring out the m, we get mg plus a. And depending on if ma is positive or negative, we will experience a greater apparent weight or a smaller apparent weight. So we'll be feeling heavier or lightweight depending on the acceleration of the system. Okay, so let's do a practice problem about what we just learned. A person of mass 45 kilograms is standing on a scale in an elevator. The scale reads 621 newtons. What is the direction and acceleration of the elevator? Okay, so the first step obviously is drawing a free body diagram. So if there's a scale in the elevator and a person on this scale, the normal force is what the scale reads. That means the normal force is 621 newtons. We know that there's a gravitational force pulling downwards, which is mg. And mg for this person is equal to 45 times 9.8, which is equal to 441 newtons. So, finding the F-net equation, we know that N minus mg will give us ma. And N is 621, mg is 441, and dividing by the mass of 45 kilograms, we can get acceleration. Plugging this into our calculator, 621 minus 441 divided by 45 gives us an acceleration of 4 meters per second squared. Okay, so now we went over apparent weight, and I wanted to go over a two-dimensional, well, not exactly two-dimensional, but some difficult force problems, which we will just use variables to solve. So, if you ask me, the first one that we're going to do is the most difficult, and then the second one is an inclined plane in which you've already seen. But the practice that we're going to do is being able to solve these both in just variables. Okay, so the first question is asking a force F is pushing 3 adjacent blocks along a frictionless surface as shown. So I will draw these 3 blocks. Our first block is M1. Second block has a mass of M2. And our third block has a mass of M3. And a force F is pushing them. Okay, so part A is asking, what is the acceleration of each block? Okay, so now this is where it gets a little scary. Everyone's like, okay, we have so many variables. What do we do? Well, this is the good thing about a system. If we take the 3 blocks to be one system, we see that there is one force acting on the system, and that force is F. If the 3 blocks are in one system, then they have to have the same acceleration. So, using Newton's second law, we know that F equals ma. The m of our entire system is equal to m1 plus m2 plus m3. And the force acting on that system is equal to F. Okay, so in order to simply solve for acceleration, we have to do F net divided by the m of the system, which gives us an acceleration of F divided by m1 plus m2 plus m3. So once again, the reason that we were able to do this is because we can take these 3 blocks as one system, because they're attached together. They're not physically attached together, but if, for example, if we're pushing 3 building blocks together, those 3 blocks move in unison. And we can take that as one system in which the total mass of that system is the sum of all the masses of each component. And the only force acting upon that system is F. Okay, part B is asking, what is the magnitude of the force that M1 exerts on M2? Okay, so here's another thing to keep in mind. Inside one system, we can have a bunch of different forces acting upon all the different components in that system. However, those end up canceling out to zero such that the net force of that system is zero unless an external force, which in this case is RF, acts upon it. So what question B is asking is finding the internal force magnitudes. So we can separately draw these like so. We can draw the blocks separate as M1, M2, and M3. We already know that the F is acting directly on M1. However, the F is not acting directly on M2 and M3. There's different contact forces occurring due to the other blocks being pushed on it. So when M1 is getting pushed by a force F, it pushes M2. And it pushes M2 with, let's say, an unknown force, which we will call F1. According to Newton's third law, if M1 pushes on M2 with a force F1, then M2 must push backwards on M1 with that same force F1. Okay, so now we also know that M2 is pushing upon M3 with an unknown force, let's say F2. And because M2 is pushing on M3 with a force F2, then once again, according to Newton's third law, there must be a force backwards that is the same magnitude F2 on the mass M2. So, B is asking for the magnitude of the force that M1 exerts on M2. So it's asking us to find F1. We already know the acceleration, so we know that the F net of each specific block has to result in its mass times the acceleration that we already found in part A. So let's take a look at M1s. We can choose M1. M1's F net equation, which we can call F net 1, is equal to F minus F1. And let's say that right is positive and left is negative. Okay, we know that the net force should result in ma, and our acceleration is F over m1 plus m2 plus m3. And this is our a, so times our m would be m1 because we're looking at the F net equation of our first mass. So now what we have to do is isolate F1. So moving the F1 to the right side and our MA to the left side, we get F minus F times M1 divided by M1 plus M2 plus M3 equals to F1. I'm not going to go over in how we simplify this, but when we simplify this equation on the left side, we should get F M2 plus M3 divided by M1 plus M2 plus M3 as our F1 equation. Okay, part C is asking what is the magnitude of the force that M2 exerts on M3? So we can either use the force net equation that's acting on the second block, which is mass 2, or we can use the F net equation that's acting on the third block, M3. I would use the forces acting on M3 because there is only one force. So our F net is just F2 equals to MA. Once again, we have our acceleration, which is equivalent for all three blocks. So MA would be equal to M3F divided by M1 plus M2 plus M3. So that would be the force M2 exerts on M3. Okay, so our last practice for 2 dimensions is another inclined plane. And it's asking us, given the following diagram and information, find an equation for the acceleration of the block, and friction is not negligible. And also the coefficient of kinetic friction is mu. So in our previous video, we went over how to draw the free body diagram of the inclined plane and how to break up forces into components in order to solve. So before we go any further, obviously, we have to draw a free body diagram. So taking the center of mass, we have mg perpendicular to the surface of the Earth, and the normal force perpendicular to the surface of the inclined plane. We have our friction force, which was already drawn for us, and that is it. So we have to choose where we want to make our x and y direction. So for me, in this type of problem, I want to make my y and x direction in this form. So let me draw that a little better. So I want my x to be parallel to the surface, and I want my y to be perpendicular to the surface of the plane. So not of Earth, but of the plane. So if I were to draw this out in a format that was easier to see for me, our forces would look like so. If this was the center of mass, this would be our normal force. This would be our mg, and this would be our friction force. Let me remove those. Okay. One more thing we're given is the angle here. And using the triangle knowledge knowledge of triangles, similar triangles, if we drew a triangle like so, this would have the same theta as our plane. And because this is a right triangle, the angle here would be 90 minus theta. So the force of our gravitational is acting 90 minus theta below the horizontal. Okay, so now let's take a look at our F-net equations in both the y component and in the x component. Okay, so since we have taken our y component as perpendicular to the surface of the incline, we know that our box isn't flying off the incline. It's just sliding down it. And this tells us that the net force equation in the y component must equal to 0. So our N force is already in the y component, and mg for the y component is going to be equal to mg sine of our angle, and our angle is 90 minus theta. This, if you've taken trigonometry or algebra before, you should know that is equal to cosine of theta. So this tells us that if we take upwards positive and downwards negative, our F net y equation is equivalent to N minus mg cosine of theta, in which this net force equation equals to 0. Okay, now we know our F net y equation, and we need our F net x equation in order to find our acceleration. That is because we've taken our x to be parallel to the surface of incline, and we know our box is sliding down that surface of incline. So, if we take right to be positive and left to be negative, our F net x is equal to the x component of our gravitational force, which is mg cosine of 90 minus theta, minus fk. And this is equal to ma, that's because we know our mass is not sliding down at a constant velocity, nor is it just stationary. However, there is some simplifying to do here. First of all, Cosine of 90 minus theta is equal to sine theta. So the x component of our mg is going to be mg sine theta. This sounds a little counterintuitive, but that is because the theta they give us is not directly below or above the horizontal of the vector of our gravitational force. And if we open frictional force into the equation that we know before, we know that kinetic friction is equal to the coefficient times the normal force, and this is equal to ma. However, we don't know our normal force, but we do have our F net y equation, and we can solve for normal force. Using our F net y equation, we can solve for normal force as n equals mg cosine theta. So this gives us the final F net x equation as mg sine theta minus the coefficient of kinetic friction times mg cosine theta. And this is equal to mass times acceleration. Okay, so now we have our F net x and F net y equation. And the purpose of our F net y equation was essentially to help us find the normal force. And the purpose of our F net x equation is to help us find the equation that we're looking for. And this equation is the acceleration. So, since we can factor out a mass from each section of the equation, we can cancel it out from both sides. This leaves us with g sine theta minus mu g cosine theta equals to a. And in order to make this look more nice, we can factor out the g as g times sine theta minus mu cosine theta. And this is equal to the acceleration of our block on the incline. So that was pretty awesome. Thank you so much for watching, and I hope this video helped you understand apparent weight and two-dimensional forces a little bit more. Our next video is going to be going into tension. So that is going to give you a new set of problems to be able to do. Thank you.